Okay, so we're going to go on to the next video, part 131. It's line 18, a3t Gluon, spin, quark, Z bosons, eRHIC, it's eRHIC, coefficients, hadron rings, and Wow Seti. Okay? So again, all of line 18A has been broken down into lots of videos. There was only 25 before. I think we got about almost 50 on this one. And it's a lot of data, so I had to break it down to make the videos smaller because they were getting up to about 30 minutes of video, and that's just too long for you and too long for me too. So this is a picture that I found, and it's about a gluon because I want to know what it was. So that's what it looks like right there. So I Googled it to see. So this is a head collision of a quark, the red ball, from one proton, the orange ball, with a gluon, the green ball. Okay. From another proton with opposite spin. Spin is represented by the blue arrows circling the protons in the quark. The blue question marks circling the gluon represent the question, are gluons polarized? The particles ejected from the collision are a shower of quarks and one photon of light, the purple ball. I don't see a purple ball. Oh, purple ball is at the top. Oh, that's the Y. Interesting. Okay. So I looked in your blog forums because I'm always Googling those words. And I found a forum where physicists talk. And this guy's name is Spud. November 4th, 2006. Radium wrote, "Hi. What exactly is a gluon jet? I've done an extensive Google search and haven't been able to find out what it is. There are no websites with definition for gluon jet." And then the answer was, according to QCD, the primary quarks emit gluons, which in their turn can emit E plus E minus minus pairs and gluons. Thus, the branching process of jet evolution appears. The gluons with high enough transverse momenta can create gluon jets. And it's HEPH-PH030-401. Spud Suvik. November 4th, 2006. Radium wrote, same question again. And what exactly is a gluon jet? So he gets a response from someone else. Gluons, like quarks, cannot exist freely at detector energy scales and must form hadronic bound states. In other words, when a gluon is produced in a collision, it must decay into quark-antiquark pairs, which in turn must dress themselves up into respectable hadrons like pions by creating more quark-antiquark pairs from the vacuum. One could, in principle, create any number of pions from an energetic enough original gluon. These end pions show up in the detector calorimeters as highly collimatal sprays of energy. In this case, they are called gluon jets. Suvik. And that was from thephysicsforum.com. Okay. Then I found a graph here that says angular coefficients, Z transverse momentum, GeV-C. Okay, so the points are the measured angular coefficients, AO and A2. As a function of Z bosons transverse momentum, the back curve is the standard model prediction, which is approximately 70% quark-antiquark. The Q bar is in green and 30% quark gluon, QG in brown. There's the brown line up there. So obviously this has something to do with creating particles for speed, right? And this is from the final government publication today. So I looked up Z bosons. I wasn't sure what they were. So Z bosons are produced at the tevatron through collisions of the particles, quarks and gluons, inside the proton and antiproton beams. Once Z bosons are produced, they decay into lepton-antilepton pairs, example electron-positron or muon-antimuon. These leptons are correlated because they are produced from the same Z boson. There is also a connection between the lepton and the Z boson polarization, the particle's internal spin. Scientists can infer information about the particle's polarization by looking at the properties of the lepton. When CDF detects the decay products of the Z boson, experimenters use the location of the particles in the detector to learn more about the mechanisms by which they are produced. Then I found another quote. The physicists then converted the result into angular coefficients, numbers that one can relate directly to standard model calculations. The most significant coefficients labeled A0 and A2 in the figure above are equal. This consistency is called the Lamb-Tongue relation. It implies that the gluon has an intrinsic angular momentum spin of 1. The analysis of the measured distribution and the number predicted by the standard model agree, which means that the standard model calculations accurately predict the observed fraction of quark-antiquark versus quark-gluon scatterings. So that's from the standard model from the Physical Review Letters, edited by Andrew Barrett-Fez. And here's the tags you're going to find in this video. All the topics we'll be talking about. And I got some more there. Look at these guys. These guys are the ones that have been working on this work here. These physicists are responsible for this analysis. First from the left is Jian Han, Willis Sakudamoto, Ari Bodek, Yeon Se Chung, Howard Budd, and Kevin McFarland, all from the University of Rochester. Thank you very much for publishing your remarks, because I used it for my video. So I could find out what this stuff was. So keywords found in the Wow Seti lines are coefficient, spin, and quark, high energy particle physics, ions and protons have come up before, neutrons as well, the theory of quantum chromodynamics, QCD, electromagnetic force, mass, Petra accelerator at DESI, high energy electron-positron collisions, wavelength, wave functions, quantum mechanics, momentum exchange, Lorentz contracted, nucleus, vector mesons, photon splits, quark-antiquark dipole. Again, when we do the cross-referencing, we're going to see what these keywords mean and what they pair up with to see if we can come up with some new formulas with that. So this is the proposed layout of the eRHIC, the eRHIC thing. The electronic ring red would be added to the existing hadron rings, blue and yellow. And it says, okay, so this is your dedicated detector, beam dump, polarized E-gun, E-star, E-phoenix, coherent E-cooler. This thing's humongous. 100 meters is this much. And look how big this sucker is. It's huge. And then we got this here. We got the range of existing E plus P data, fit to data value Q2. I don't know what all this stuff means. I saw this pretty graph and it talked about what we were talking about, so I wanted to show you what it looked like. Okay, so these guys here, eRHIC, an ultra-high resolution electron femtoscope by Salvador Fazio, Tobias Toll, and Thomas Burton. And that's the three guys there. They are postdocs and working in the EIC task force. eRHIC is a proposed upgrade to RHIC involving the addition of a high-intensity electron beam which will collide with one of the existing hadron beams. Such an upgrade will open a wide new frontier of precision hadron physics for the RHIC facility. To date, the only lepton proton collider was the Hera accelerator and operated at the DESI laboratory in Hamburg, Germany until 2007. This is very important. The reason I'm mentioning these different places and what they can do is because these colliders are probably going to be testing some of these theories that I'm posting. I'm not sure if they can do it all, but I'm hoping they will, to see what kind of results they get from them. Among its important contributions are measurements of the momentum distributions of partons, quarks, and gluons in the proton via the process of deep inelastic scattering, DIS, see figure. So this eRHIC thing tests things for quarks and gluons. It tests for the speed of them, and I'm not sure what they do with this stuff, but they do publish their results. And it could take quite a bit of time for them to work up all the information. Some of them take 4 or 5 years to post whatever they're working on. So it's a long process. eRHIC is intended as the next generation lepton, proton, and lepton nucleus collider. So they're working on advanced technology. Okay. Basically what they're doing is testing things. They're posting their results, but they still haven't quite figured out what to do with the results. What can they use it for? So I'll be pulling some of their data to see if we can use it to create this high energy UFO engine. The machine will provide polarized electrons with energies of 5 to 30 GeV, polarized protons with energies of 50 to 325 GeV, and heavy ions at up to 130 GeVu. These beams will collide at a luminosity of the order of 1034 interactions, or 1034 interactions, centimeters, I don't know if that's squared, S to 1, I don't know how you would read that, but more than 2 orders of magnitude higher than at the HERA. The new dedicated eRHIC detector will be nearly hermetic and will deliver high energy, momentum, and angular resolutions. This is going to open the opportunity for very high precision measurements, allowing detailed investigations of the proton and nuclear hadronic substructures, as well as the spin structures of nucleons. So they'll be using their information and working probably with CERN and comparing notes. So this is the electron, photon Q, proton, and a quark. Shows how it's created. So probing the gluon content of ions and protons at small x. There's the small x there. Protons and neutrons are bound by the strong nuclear force, which is mediated by gluons and described by the theory of quantum chromodynamics, QCD. Unlike photons, which mediate the electromagnetic force, gluons can interact with each other. It is this self-interaction that generates around 99% of the visible mass in the universe, while only the remaining 1% is provided by the intrinsic masses of quarks. The existence of the gluon was experimentally confirmed in 1979 at the Petra Accelerator at Decay in 3 jet events in high-energy electron-positron collisions. Even though gluons were discovered 3 decades ago, the force they mediate remains the least well known in the standard model of particle physics. Now, isn't that interesting? They've been testing this for over 35 years, right? And they still don't know how fast they can make these things go. But when I give you my formulas, you're going to find out how fast they can go. Out of the outstanding puzzles in our understanding of the theory of the strong interaction is its behavior at small values of x. At here it was found that at small x the proton's content is dominated by gluons. Small x means a gluon carries a small fraction of the proton's momentum, which means that the momentum is shared among many gluons. However, there is a puzzle extrapolations of the present measurements to ever smaller x yield an ever rising gluonic cross-section. Thus, this gluonic part of the cross-section will eventually become larger than the total cross-section. Now, this is too much reading. Okay, forget it. Anyways, you can read some more about it, but you probably know about it anyways. But I was reading it to find out what it means. So you want to go to www.bnl.government and just look up this information here. So it describes how it works. So measuring the momentum structure of the nucleus. Here's a graph here. I had all these nice and big. I don't know how they got so small again. Spooky computer here. So a measure of gluon density within protons top and elite nucleus is the bottom. Purple means dilute and orange means dense. Okay, and this is in relation to HERA and eRHIC again. So it says one of the key measurements in electron collisions at eRHIC is also one of the simplest. The measurement of the scattered electron alone while ignoring all other particles produced in the interaction. Okay, and these are called structure functions of the nucleus or proton. And blah blah blah. That's www.bnl.government. And we have this photo here: electron, virtual photon, momentum, and proton. In a diffractive event, the proton or ion stays intact in the collision. There may, however, be an exchange of momentum between the proton and electron. So, And there's spatial mapping of the nucleus, quark-antiquark dipole, momentum exchange, photon and nucleus. An exclusive production of vector mesons, the virtual photon splits into a quark-antiquark dipole which interacts with the nucleus diffractive. So quark-antiquark dipole came up a lot too in the Wow Seti lines. So the spatial distribution of protons within the nucleus has long been known, but how are the gluons in the nucleus distributed into space? So that's a question they have. They're saying it can be determined by diffractive events, and that's why they're testing these. They're still trying to figure out what's in the dark matter in the universe, and they measure these things to find what the exchange momentum is. Talks about RHIC is going to be equipped with a full acceptance detector. It's going to be able to measure inclusive, semi-inclusive, and exclusive reactions. TMDs can be extracted from the semi-DIS data for different spin-dependent and spin-independent observers. So you're going to see how they spin and not spin. And this is basically the different testing facilities. And I put it in there because DESI, CERN, and BNL and JLab all came up, and they're also in the Wow Seti data as well. So the GPDs left and TMDs right provide a 2+1 dimensional image of the gluons in the nucleus. That's what they look like. Okay. The contributions of the gluon spin has already been a topic of intense study in both the experiments at the DIS and RH Phoenix and STAR. The gluon spin contribution can be determined from measurements of the gluon helicity polarization, the difference in the number of gluons polarized along versus opposite proton helicity. Okay, no. And this one here, there's that graph again. The distribution when integrated over X gives the contribution of gluon spin to the proton spin. So that means, quote, measurements by experiments such as Herms, Compass, and Bell. I had Bell come up in line 18, A3, 5 or 6 videos ago, have demonstrated that a number of such distribution functions exist, but present data is rather limited in its precision. The reason I posted that is shows that even though they're testing things, they still don't understand the data that is coming up or the results that are coming up. TMDs are of interest not just for the relation to the proton spin, but because they allow a three-dimensional imaging of the proton in both longitudinal and transverse momentum space. February 17th, my thoughts. This section is all Greek to me. I cannot figure out what it means, but it does talk about particles being split and studied, just like the neutrinos. It almost sounds like they want to build something to test the gluons on a more extensive level because there are particles found in our universe as matter. I wonder why this is so important to them. Is the matter holding them back from traveling quickly in space? I wonder. Okay, so that's the end of that video, and we'll go on to the next one.